All right, let's just jump right into this explainer. If you've ever stared at a physics problem with moving parts, friction, gravity, the whole shebang, and just felt totally overwhelmed by all that information, well, you're in the exact right place. Today, we're doing a complete step-by-step tutorial on force diagrams based on our sources. By the end of this, you'll know exactly how to take all that real-world chaos and magically turn it into clean, simple, solvable math. So here's our roadmap for today. We'll start with the secret weapon, touch on Newton's borrowed laws, go over the rules of the diagram, meet the forces, build your very first FBD, and finally, get to the mathematical payoff. Section 1, the secret weapon. Let's talk about physics problem solving. There's this really fantastic quote in our sources that I absolutely love. It says, "The diagram is not extra work, it is the work." Now, this is a massive mental shift, right? Because normally we kind of think of drawing a picture as just a little side quest before we get to the quote-unquote real math equations, but actually that's completely backward. As our sources point out, if you take the time to draw a clean diagram, you're going to solve the problem. If you skip it, well, you're basically just guessing. The free body diagram, or FBD for short, literally is the work. It's the absolute crucial bridge you need to cross to get from a messy word problem to that final correct mathematical solution. Moving right along to Section 2, Newton's borrowed laws. And yeah, there's a pretty surprising history here. So looking at this historical timeline, it actually turns out Isaac Newton was kind of late to his own party. You know, we always talk about Newton's first law, the law of inertia, right? Well, look at this. Isaac Bateman was already writing about inertia in his journal back in 1618. That is 69 years before Newton published his Principia. And then René Descartes improved on it and published similar ideas in 1644. So Newton's first law wasn't entirely his own invention. He was absolutely standing on the shoulders of these earlier thinkers. And because of that messy history, and because tricky words like inertia can totally confuse students into thinking it's an actual physical force, physics educators really recommend a shift in how we talk about this. Instead of getting bogged down in those old historical names, the experts suggest we just focus on the law of cause and effect. This approach directly links a net force, which is the cause, to an object's acceleration, which is the effect. Once you make that mental switch, it's a total game changer. Which perfectly brings us to this beautiful little equation, F net equals ma, force equals mass times acceleration. This right here is the mathematical engine that our diagrams are going to power. Ultimately, the entire goal of drawing a free body diagram is just to figure out that F net part, the total net external force acting on whatever system we're looking at. All right, Section 3, rules of the diagram. Let's get into how to actually draw these FBDs. Okay, so every single time you draw one of these, you have to follow these exact steps. Step 1, you model the object as a point particle. So just a dot or a simple box representing its center of mass. Honestly, it doesn't matter if it's a car, a heavy rock, or a person, it all just becomes a single point. Step 2, you represent the external forces using vectors, arrows, that start exactly at that point and point away from it. And step 3, you draw a coordinate system, where the direction the object is actually accelerating is marked as positive. Now, while you're drawing, you always want to ask yourself this one guiding question. At this exact moment in time, what is pushing or pulling on the object? You have to think like a detective here, hunting down every single interaction. Basically, if something isn't physically touching the object, aside from gravity or other invisible field forces, of course, it absolutely does not get an arrow. On to Section 4, meet the forces. Let's open up your physics toolbox. So this table neatly lays out the specific forces you're going to encounter most often. Notice the symbols we use. You've got Fa for an applied force, like, say, a person pushing a refrigerator. There's Fn for normal force, which is that perpendicular push from a surface, like the floor holding you up right now. Ft is for tension, from things like ropes. Ff is for friction, which is always opposing motion. And finally, Fg for gravity, which is just the constant downward pull from the Earth. But before we actually start drawing, keep these basic rules of engagement in the back of your mind. First up is the air resistance rule. Always assume there is no air resistance unless the problem specifically mentions it. Trust me, that alone saves us a ton of unnecessary calculations. Second, your arrows do not need to be drawn perfectly to scale. They just need to be roughly accurate to show relative sizes. Oh, and finally, this is a great rule of thumb for tension. You can't push a rope. Ropes and strings only pull, period. Section 5. Building your first FBD. Time to start visualizing these forces. Okay, let's look at a side-by-side comparison here. On one side, we have a messy, real-world sketch of a falling rock, maybe with some little cartoon motion lines to show it's dropping. But on the other side, we have its abstract free body diagram. Do you see how that complicated real-world rock transforms into just a clean little box? We add a downward vector for gravity, Fg, and since this specific scenario actually mentions it, we add an upward vector for air resistance, Fair. It's clean, it's simple, and notice how both arrows are pointing directly away from the center. And this approach shows us exactly how to handle way more complex systems too. Take a situation with a person pushing a loaded cart. You do not want to draw one massive, confusing diagram for that whole shebang. Instead, you break it down. For system 1, you just draw the cart, giving it specific arrows for the floor's friction, the normal force, the person's push, and the cart's weight. Then for system 2, you just draw the person with their own completely separate set of forces. Deconstruction is literally the key to clarity here. Finally, section 6, the mathematical payoff. Let's calculate that net force. So naturally, we have to ask, if the diagram isn't extra work, but is the work itself, how does it actually produce our final numerical answer? Like, how exactly do we go from a drawing of a box with some arrows sticking out of it to solving F net equals ma? Well, it turns out the diagram practically writes the math equation for you. You never have to guess. All you do is separate your forces into horizontal or x direction forces and vertical, y direction forces. If your arrow points in the positive direction of the coordinate system you set up, it's positive. If it points opposite to that, it's negative. Then you just sum them all up. Finding F net is quite literally just adding and subtracting the arrows that you just finished drawing. And you know what's really cool? This whole diagramming process actually reveals some hidden truths about the universe, too. It shows Newton's third law in action. For instance, think about an apple hanging from a tree branch. The Earth pulls down on that apple with gravity, right? But the very logic of our diagrams dictates that there absolutely must be a reaction pair. So I'm going to leave you with this somewhat provocative thought to chew on. Based purely on Newton's laws and the universal gravitation diagrams we've just explored, if the Earth pulls down on an apple, that tiny little apple is actually pulling the entire planet upward with the exact same amount of force. I know, it's totally mind-bending, but the diagrams do not lie. Thank you so much for joining me on this explainer. And hey, keep drawing those vectors.